So the multiplier algorithm that we discussed yesterday, right? We would like to capture that. So did anybody try? Anybody try to do it? Okay, let us try writing a module for signed shift and add, not signed, shift and add multiplier. Since it is a sequential circuit, we'll need a reset and a clock. And we will also need the multiplier. So we could write a type definition of we need a multiplier, we need a multiplicand, and we will produce a product and maybe finish. Right? Multiplier is an input, multiplicand is also an input, product is a output, finish is an output. Correct? We need to then go ahead and declare that the reset in is an input and clock in is also an input. The multiplier in and multiplicand in are both, let us say, bit. Product out is, it will have twice the number of bits. And finish output is on. Okay, I hope this is clear to everybody. Now the multiplier will respond to events like positive edge of flip-flop, I'm sorry, reset, or positive edge of clock. If we are trying to do a reset, then first we have to, I think we forgot to declare the registers. So maybe we'll create a register called A register, then Q register, and M register. Then we will need a counter. So the counter can be C log 2 n minus 1. C log n inclusion. So we'll give one extra. So we load with initially we would like to load the multiplier into M and into Q. Multiplicand into M register, right? And then accumulator is initialized to 0. And count is initialized to N. So these are our initializations when we do a reset. So all the registers are loaded, and yeah, if it is not the reset, right? Then we have to check what is the value of Q. Sorry, Q0. So if Q0 is equal to 0, if Q0 is 1, we add, otherwise we shift, right? So let us check for 1. If Q0 is 1, I had to add A and M, right? That would result in a 5-bit number or a n plus 1 bit number, which will store in Q and a carry. So we'll have to declare Q somewhere. Else, we could say the only thing we want to do is C equal to 0. C will be 0 because we may have to shift later. See, here we'll have the same problem. I think we will have to do 2 equal. If I do shift immediately, then the old value will get shifted. So we'll have to give equal. So then we can say uh, A and Q equals C to, I'm sorry, A and Q equal. So what we have done is we have brought C from the right hand side. We have shifted C in A has remained, A also got shifted. Then Q3 to 1 got shifted, right? So these are the things we have been able to do. So this happens either if reset is 0, I'm sorry, either if Q0 is 1 or 0. So for both Q0 equal to 1 and Q0 equal to 0, we do this. Then we can reduce count, and somewhere count will become 0, and we can assign finish to count equal to 0. So finish will become, and I suppose product out will be AQ. So the concatenation of A and Q will go into the product. So we declare the reset and the clock as inputs. I guess we have to declare this also as input. Input, this is also an output. This is an output. These are internal, we can declare them as bits, etc. Then if reset is high, we are initializing the registers. If it's a clock that is coming in, we check what Q0 is. If it is 1, we add, then shift. Okay, let us assume that this will work. The module multiplier test, right? So we'll instantiate one copy of the multiplier here, shift and add multiplier. So the reset main is going to be declared here. Okay, and then bit. So let us say we are doing this for 4 bits, and let us say we have multiplier main and multiplicand main. Then we can include one more bit called product out and finish out. So we'll bind these guys over. So dot reset in is sent to reset main. Dot clock main is connected to clock main. Dot multiplier main, multiplier in is connected to multiplier main. Dot multiplicand in is connected to multiplicand main. Dot Product out is connected to prod main dot finish out is connected to fin. So this is our binding. Then we can test it with one case. So we'll start with maybe multiplier main equals maybe 5 bits. 5 multiplicand mean is 6. Initially, we'll set reset main to be 0, clock main to be 0. Then we'll reset this guy. Okay, we'll reset this system. And then we'll repeat 4 times. We'll apply a clock of period time. Here we can display multiplier so we'll keep displaying it and it close it. Improvements. Okay. Let us make sure that we are displaying the registers also. So initially we had multiplier 1, so it added 1 and shifted it. So 6 was added and it was shifted, and 2 is 0. So there's something gone wrong with Q. Why is Q coming in? What am I doing now? Multiplier main, multiplier C is percentage B, no. So this is plus, so I'm not C, C, C. Mistake. So initially, this was the initial value. Then we saw this 1 and we added multiplicand to A. There's something wrong. A is equal to A plus 6. So you know this is C A. This is C A. So we know it's right. Sorry, that was a mistake. We can display this in electrical. So multiplication of 5 and 6 gives you 30. Let us try 7 and 7. And then Try 0, try 1, then try 7 and 1. The reason I did 5 here, could have done 4, but what is happening is as soon as the clock goes high, immediately we're displaying. Okay, so as a result, I have to give 4. The alternate is maybe you can give 1 unit delay here. That will also work. So immediately after the clock wants display, but wait for a little extra time. So then 4 clock pulses will be enough. Okay, as soon as the clock comes, the things don't change. Okay, it takes a little fraction of a second. I mean, little time is required. Something other than non-zero to display. So ask me questions. What are the questions you have? Let me ask you guys. Mangaldeep. Mangaldeep, can you explain this part? Poonam Kadam. Okay. Dr. Poonam, can you explain this part? What is happening here? Are you not able to unmute? Oh, okay. Today, I think they are not able to unmute. So, what is happening here? See, we declared a module called shift and add multiplier, which is parameterized. Okay. And n is set to 4, which means we are trying to build an n by n shift and add multiplier. And what are the inputs to it? Reset, clock, multiplier, multiplicand, and the outputs are product and finish. So we described all of them, right? So we described reset and clock. We described the multiplier and multiplicand as n-bit numbers. These are unsigned numbers. Similarly, product is an unsigned output of 2 n bits. Finish is a 1-bit output. We have declared internal registers A, Q, and M. And we have declared a count which is 1 plus log n bits. We need 1 extra bit because we are going to initialize it to n. See, n cannot be fitted in a log n bit register. Okay. So we need 1 extra bit. Then we need 1-bit register called C. Finish out is nothing but when count becomes 0, we have done. We are finished. And product is in A and Q registers. The circuit checks for the reset and clock. And this is the initialization. where we load the Q register from the multiplier, the M register from the multiplicand. A register is initialized to 0 and count is initialized to N. Then when the clocks arrive, we check Q naught. That is the algorithm, right? See, we are doing sequentially. Q gets shifted to the right. Okay, at the end, we are also shifting Q to the right. So actually, all the bits of Q will get tested, but one at a time. So initially, Q0 is tested. Then when you shift in, Q1 will come in the position of Q0. So Q1 also will get tested. So one at a time. This is not a combinational logic. This is sequential logic. So we test one bit at a time. So Q0 can be either 0 or 1. If it is 0, we simply have to shift A and Q. The shift operation is achieved like this. A gets shifted to the right by one bit position. The carry comes and occupies the leftmost position. And Q3 to 1 will occupy the last three positions. So this is our shift operation. If you want, you can say shift A and Q. If Q is 1, then we have to add A to A. A should become A plus M. And the carry that comes from that will also have to, sit here. So that is what is happening here. Add M to Q and store the carry in C. And at the end of all the this logic, we have to do two things. We have to shift in either case, irrespective of whether Q0 is 1 or 0. We do a right shift, and then we subtract count. Right? Any doubts now?
Sir,
Yeah.
sir, this addition happen internally in with integer or in binary?
See, it's just a representation, no? It will be binary only. It's binary only. We can print it in either way we want. Numbers are stored in binary only. Is it okay? See, A has been declared as a n minus 1 colon 0.
No, I'm asking the operator plus.
Plus is a high level operator. The Verilog understands that A is an n bit register and that M is a 1 bit register, n bit register. So it knows how to add n bit registers.
Okay, sir.
If you don't want to do this, if you want to go down to the level of hardware, see, this is a behavioral description. Okay? If you
Yes.
want to go to the next level and say, look, I'm going to build my own adder, then you will have to create a module called ripple carry adder or something like that, and you can add it
Okay,
here,
okay, okay.
right?
Yeah.
So you are welcome to do that. See,
Yes.
this is a behavioral model. We know we don't want to get into how the addition is done, but we know
Thank
how
you,
to
sir.
do it.
Yeah.
What about the others? Dr. Kadam, are you clear? Okay. Any other questions? We can try increasing the size of the multiplier. Okay. So we can say shift and add multiplier with maybe 6 bits. Right? So we'll have to make this into 5 to 0. And product will be 10. So here we can try multiplying 17 and 33. So no other changes are required. So we can go ahead and try. There is still somewhere we have
Sir, product how many bits, sir? 6 into 2, no?
six. It should be 11 bits. Sorry, yeah, 12 bits or 11 bits. Right. It was a mistake. So there is an error here. It is a reason. You see, we do have these kind of problems. Sometimes we have not. Somewhere there is a. What if it is 7? Oh, you know what? I think no, I know the mistake. This is 6 is okay. See here the clocks are insufficient. We should do fixed clocks. Hmm, okay. Even then there is wrong. Just check. Hmm, we took a 6-bit register. Hmm,
Can we use parameter in the test bench also?
Huh? Have I hard coded something?
Sir, can we use parameter, this like capital N in the design? Can
Yeah.
we use the same in
No,
the
that is
test
okay.
bench also?
No, no, that is okay. This can be 4. We have to modify here only. If I have hard coded something here, it will not work. I don't think I hard coded. Here. This is a mistake, no? This should be n minus 1. Okay? See, you should not hard code anything. Can you see now? So 17 multiplied by 33 is, I think this is the correct answer. Right? So try 8. So the correct way to do it be define maybe m to be 8. So this will be m minus 1. This will be 2 times n minus 1. This will be m. These are some new random range. Let us say 0 to e to the power n minus 1. New random range. And then this should be. So everything can be in terms of n. So hopefully there is nothing else which is, so it multiplied 146 and 64. So verify that this is correct. So we can try, but unfortunately, U-random range, um, I don't think I can change its behavior. Next time, the only way I can do it is I can repeat this. Right? I can try and repeat this whole thing. This time it will take a different. So this time it multiplied 4 and 49. Right?
Sir, how will you ensure here all corner cases are tested?
So we tried, no? We tried. See, right now we are doing random tests. So we tried multiplication by 0. We tried multiplication by 1. Corner cases, and you'll have to. You can rewrite this. See, you should not. If you don't want to do random testing, you can create your own test cases, right? And repeat. You can store your test cases. Use something like a dynamic array or something like that, and store those values.
Okay.
And then you have to do it for each of those. That is the reason why those data structures are available.
Okay.
So, is it clear?
Yes, sir.
So these are, see, we found bugs, right? See, I had made a mistake here. That 3 was there by mistake, right? So we will have these bugs. See, unfortunately, only when we tested. See, if we had not tested the case of 6 or something, that bug would have stayed there. Okay, this is the biggest mistake that we make. Okay, we test a little bit and we say it's okay and we go on, right? But there will be a lot of bugs that are there because of insufficient test. Clear? So this is the number of tests. How do you suppose I don't want to print so much, right? So what I can do is I can check if multiplier main multiplied by multiplicand main is not equal to product, then display. And we can move that here after the additions are, after everything is complete. So go ahead and apply all the clock cycle and then check if multiplier main multiplied by multiplicand main is not equal to product main, then display. So this time nothing should come as the output. So now you can afford to put maybe more test cases. So it is multiplying. It will apply this 30 times. Okay. So you can see that 30 random pairs of multiply numbers were represented. They are multiplied, and in each case, it did not give. So that improves our confidence. So we can even say, let us do 300. Okay. I don't know whether we'll be able to do. This guy will not give you more than certain. Okay. So can you see? We applied 300. So our confidence just improves when we apply a lot of random values. See, because this is an 8-bit multiplier, so the number of test cases is huge. Right? questions in this? Could you follow?
Sir, I have a doubt from yesterday class. One doubt.
Ah, go ahead.
Sir, that full adder you designed, no? The last
Ah,
you declared logic, all these things. Then like this, you told when multiplier and multiplier product is not same, then do like that. You have written a statement. You are finding the carry out and sum out. That
yes.
statement, when I say always carry output is zero and sum out is one. Mm, we are doing full adder,
Uh,
then let's say we are having 8 combinations. For each
mhm.
combination I get a carry out and sum. For
Yes,
combination number 1 2 4 7, sum should be 1, and
yes.
for rest of the this one carry out accordingly will be calculated. We have two assignment statement,
Mm.
but from your statement carry
Mm.
output equal to 0, sum equal to 1, how it demonstrate that all answers are will be coming correctly? Did not understand that point. Shall I put that statement, sir?
No, I can't understand unless you show me the code. If you show me the code, I'll understand.
So this was there yesterday. One statement before while
Yeah, you
displaying.
can share it. You can share it and
So I put in the chat box. If you see this one, you'll understand. Dollar display input equal to percentage D carry output and sum output. When I run the cases, I got all the cases carry output equal to 0 and sum output equal to 1.
so, display statement. Huh?
Ah,
You
so
are you
from
are
that, yeah, from that you are concluding that it is tested properly. Then what I did
no, no,
was
you
in a
just
regular.
no, no, you show me the full code. Just don't show me the display.
Okay, okay, sir.
No, no. See, you show me my code here. I don't
Ah,
want to see the output.
okay, sir. Code also I put actually before
Where
that.
I only saw the display statement.
Ah, okay, sir. I put. Sir.
Oh, oh no, no, it's here. I'm sorry. I'm sorry. I saw it here.
My only doubt is that this carry
Yeah,
output
yeah,
zero
yeah.
is.
Let me just copy all of that. 1 second. Some part of it got cut off. Hmm. Module full. Ah, here it is. So module full adder.
Ah, sir.
FA bus sum out is a XOR of FA bus A in B in and C.
Yes,
And
sir.
FA bus carry out is this value. What is your doubt? It's not working?
My doubt is no, no, it's working. Output is coming
Ah,
like that. You see, no, sir. Output equal to carry out is one someone. But from there, I'm not understanding for which combination what output I am getting. Input is 0. That means 0, 0, 0. Uh, Sir, if you see the output only, there only, that's why I listed output. Can you explain me the output what I'm getting?
Let me run it. Huh?
Excellent, sir, will use. Sir, I have deleted one I there. No, no, it's there.
This is
There, this but
I'm getting input 7, you know. I don't know why you are getting.
sir, when input is
Input
7,
7 means
that
111.
that means
Input equal to 7 means 111.
correct. 6, sir. See, look, sir, always carry output y 0, sir.
Let me
I
check
want a
again.
truth table like
Oh, that
0,
means
0,
there is
0.
a bug. There may be a bug. FA bus dot in.
No, sir, bug is not there. Same code. When I try to display using A, B, C in sum and C out with the binary format, I am getting. I have a code I checked yesterday with U random also. I checked by varying. I vary quite a number of times, so I could get all. I varied for around 20 times, so I got all combination tested. I wrote down also. Particularly this main bus A dot in, main bus B dot in, main C dot in
So you know
equal to
what?
1.
This
That's
one is wrong, no? See, this should be I, right? This is a mistake.
okay. Okay,
See,
sir. Okay.
1 means it will always take 001. See, I
Okay, sir.
is what should have been there.
Okay. Now changes
You
has
see,
come. Yes, sir. Yes, sir. So that statement I
see,
could not understand.
I
Tried.
did I when I tested it also was it wrong? I equal to 1 was there.
Yeah.
Sorry, please. If that is the case, then all of you should change it. Okay, please change this to I.
Sir. Now it is. I thought something new way of you are testing it so that
No,
I
no, no,
don't know.
nothing new, nothing. Okay,
Now it is coming, sir.
okay, sir.
Yes, sir. Thank you.
Good. I'm so happy to see Professor Panda trying all these things out and verifying.
Just
Very good.
one, it was very.
Very good, sir. Very
I
good.
was comparing, sir, Verilog and System Verilog there. You
Ah,
tested this way, then I thought, why not I change very A in B in C in with E random and check.
yes, that is
Then once
exactly what you should do. That is exactly
and
what
one
you
shot
should
I
do.
did
That
not get
is
all combination. Then I started increasing combination. I got all.
okay. Good.
Thank
Very
you, sir.
good. I'm, very happy to see that you're doing that. Very good.
Thank you, sir.
Any other doubts? See, we can also try and develop a class for this. Okay. Suppose we declare shift and multiplier as a class. Then what are some procedures that you will allow on the shift and add multiplier? What are the data you will give? See, data could be a bit. No, first we have to, yeah. Let us pretend right now it is all 7 colon 0. Okay, we'll only test for an 8-bit case. Then we'll also have a product, right? And then maybe we will have a A register which is 7 to 0, Q register which is 7 to 0, M register which is 7 to 0. Let's see. Then okay, let us say we have done all this. Then what is the initialization we need to do? The initialization we can try, see, we can try function. We can try to initialize multiplicand to maybe 1 and multiplier to so on. So this is our initial value. We can create a task called load values or something like that, which loads these may not be required. Even this may not be required. Maybe count we can initialize. So when I start this guy, the only thing I'm doing is count equal to 8. I will load these things when the load is called. So we'll say a equal to 0 also we could try here. But here also we can, okay, let us try m q is equal to m flat and m equals to. Okay. So these are the two things, let us say we do here. Then we can give a function called clock. So that will check for q equal to 0. If q is 0, if q0 is 1, then do this. Then add, what do we do? C and C and A must be equal to A plus M. And maybe in either case we shift. Then we can display dollar display A equals some value, B equals some value. Then we also have to set count equal to P. And we display employer. So employer is not there at all, right? We are not storing it anywhere. Maybe it would not have been a bad idea to store it. Product is 8K. So let us see if it understands all of this. Oh. So now in the main one, I will declare shift and add multiplier as a SAM as a object of this class. And in the initial part, I will say SAM equal to new. And to my knowledge, new doesn't require any input. Right? I am not doing it. Then I'll say SAM dot load. Let us say we load 5 and 6. Then what do we have to do? We have to clock, right? We have to repeat 8 times. We have to apply clock to the SAM and we have to display. Right? So that will also, in a way, test the guide, test this algorithm. The add is missing. Load values. Here also we got the same answer. We multiplied 5 and 6 and we got that. So It's up to you, how you wish to do it. Okay? The other one may look little closer to hardware. Okay. But from a verification perspective, this is also going to verify the algorithm. Okay. We can try other load values. We can repeat this many times. So maybe we can have for I equal to 0, I less than 5, I plus plus. So I have 5 times I repeat this and I'll declare I here. And I'll declare a employer multipliers array. And we'll put maybe 5, 7, 25, 127, 33. Okay, there are 5 of these. Similarly, bit 7 colon 0 can be multiplicand array. We want to multiply 5 with maybe 8, 7 with 1, 25 with 25, 127 with uh, 33 with 33. So here instead of 5 and 6, I could say multiplier array of I and multiplier. So this way, I'm trying different test cases. And the display, maybe I can do it at the end. So this time it will try to multiply 5 and 8, etc. It doesn't like it when all the data should be together. So 5 and 8 was multiplication was 40. 7 and 1 was 7. 25 and 25 is 625. 127 times. Hmm, it's wrong, no? Oh, count I have to initialize to 0 every time. I have not been doing that. See, we are doing count equal to 0 only once, I think. We made it part of this. I think load values also should do that. But even then we will wrong. And why is count 24? Because What was the last case? 33 and 33, right? This is wrong. So count was load value A equal to 0 also may not be happening. Huh? So load value also should make A equal to 0. Can you see? 7 and 1 is 7, right? 127 times 2 is 254. Now I think more or less all the bugs are gone. So let us try 1, 3, 28, 255, 6. Let us try 3 and 0, 28 and 25 is okay. Let's try 25 times 1, 66. So 1 times 8 is 0, and then 3 times 0 is 0. 28 times 25 is 700. 25 times 1 is 255 times 1 is 255. 66 times 33 is 1. And we can also do what we did earlier. We can check if there is an error. Okay, if Sam dot, we can say Sam dot error. If multiplier multiplied by multiplicand is not equal to the product of okay, then there is an error. So you can also display errors. So if all goes well, no error should come. So I did not give any errors. So we assume that all is well. We are getting validation that the algorithm is working because we are explicitly checking if the product is equal to. Is it clear how to use a class like this? Any doubts? So somebody is saying yes, sir. Somebody is saying no, sir. So yes means yes, there is a doubt. Oh, no. Fine. Now, here is a thing that I want you to try right now, right? Please build a class for a counter. Okay. So that is an exercise you will do now. It's a very simple exercise. I want everybody to try it right now. So build a class for a simple maybe count for a counter counts from 0 to 50. So it's a very straightforward 4-bit counter. So please try it. I'll be here. So how is it going? Anybody has? Oh, very good. Dave, try showing your code. I will show your code to others. If you show it here in the screen. Here, let us look at this one. So initially we make it 0, task, run, and start, begin. The count declaration is wrong. Oh, okay, it's an integer. Okay, anybody else? Has anybody else finished? Purvesh. So tell me, what have you done? How have you done it? So this is Purvesh's code. Class counter, function new, task increment is. See, this will automatically happen. Okay. You have declared this as a 3-bit counter and 4-bit counter. So really you don't need to do this because it's a 4-bit value, it will automatically declare. Okay. Then display count equal to very good. Module counter test, initial counter CC very good. So yeah, I think Purvesh got the hang of it. So let us do it for maybe 32 times. You will see that the counter will automatically go to 0. Purvesh, did you understand? You don't need to set it to 0 if it is okay, because you have declared it as a code. If you have declared it as an integer, then you are right. Okay. If this was an int, then you have to check whether it has reached 15 and all that stuff. Anyone else? And also you should try to use the modulo. Okay. See, even if this was declared as int, so it's easy to say modulo instead of saying if then else. So now this becomes a modulo, it will do the same thing. If you just make it 10, it will act as a decade. Okay. In fact, you could take that as the, that value. Okay, that is, maybe you can say bit equal than 0, it's non-states or something like we will copy the num states value, right? And here instead of percentage 10, you will say percentage num states. And when incrementing, you can make it whatever value. Maybe you can make it 6, in which case it will act as a so this will go from 0 to 5 and again 0 to 5. Is that okay? Good. I'm so happy all of you are learning some things. Very good. Glad to know this. Indenting the code is important, huh? Because this particular editor is terrible. It modifies your indentation, but you will realize that indenting it is quite important. And it's not difficult for you to accept an increment or decrement signal. Check if it is increment and decrement. Okay, so you can do all those
Sir,
things.
it is a adder and combination circuit, sir.
Which one?
This one is a combination circuit, sir.
This is just a model. This is neither combination nor sequential.
Because
Okay.
in test bench
This
I
is
did
just a
not.
model.
Okay.
Huh? What?
Because test bench also written top module. In that clock also not there.
Yeah, yeah. This is not a circuit at all.
Okay.
Okay. This is just a behavioral model.
Okay.
Okay. A class for counter has been created to behave like a counter. You understand? It's a software model, nothing else.
Sir,
It's
class.
useful when,
Sir,
in this example, it is not such a great thing because it's just a counter. But if you have a much more complex circuit, then it is easy to build a model like this and then test it thoroughly. Then you will understand many things that can be fixed. It is so easy to modify this, right? And then when you have got this right, you can go and begin your actual hardware. Understood, no? See, when you want to do some prototyping and show to somebody how the counter will behave, they can look at this output and they'll get an idea of what your counter is going to look like.
yes, sir.
So this is not a real circuit. So I'll show you the Booth's algorithm and you can try to implement the same thing. I'll give you another example. So you may have done it if you have done your digital design class or something like that. So in Booth's algorithm, it is signed multipliers, signed number multiplied. See, when we did the shift and add, whenever we had a 1 here, we were doing add and shift. Whenever there was a 0, we will simply shift. So let us take the number 101. What is this number? It is equal to 2 to the power 2 plus um, 0 times 2 to the power 1 plus 1 times 2 to the power 0. So 101 in binary is 5 in decimal. Now I could try doing the same thing like this. I could say 1 bar 1, right? And 1 bar 1. So 1 bar means minus 1. So we could say 1 times 16, sorry, 1 times 2 to the power 3 minus 1 times 2 to the power 2 plus 1 times 2 to the power 1 minus 1 times 2 to the power 0. So this is 8 minus 4 plus 2 minus 1. And this is also equal to 5. So this is called as recoding the multiplier. Using, instead of zeros and 1, we are using 3 states, 0, 1 and 1 bar. 1 bar is same as minus 1 and 0 and 1 are the same. So another example is 110. So that is 1 bar 0 1. So this is 8 minus, so this is 8, this is minus 1 times 2. 111. This is 1 bar 0 0 1. This is 8 minus 7. So when you allow subtraction for the 1 bar, there is no unique way to represent it. Okay. There may be multiple representations for any value. But we in this Booth's algorithm, this is a recommendation. So what you have to do is, suppose we take this 110. So you add a 0 at the end. Then 0 minus 0 is 0. 0 minus 1 is minus 1. 1 minus 1 is 0. And then 1 minus 0 is. So you can add a 0 on either side. So that is what we have been doing. So 101. I have added a 0 on the right side. So 0 minus 1 is 1 bar. 1 minus 0 is 1. 0 minus 1 is 1 bar. And 1 minus 0 is 1. So if you allow multiplication, if you allow subtraction also, then it may be faster. That is the idea. So if I have a series of ones, see the earlier multiplier works worse when it is 1, 1, 1, 1. So imagine if this was a shift and add multiplier, then every one will invoke an addition. But if you use Booth's recoding, this will become 1 bar and I'll get a lot of zeros. So if I have a lot of ones or a lot of zeros, Booth's algorithm will work better. So it will do fewer additions than the corresponding shift and add multiplier. So the number of additions comes down. See, if you have this guy, unfortunately it will increase 1 bar, then 1, 1 bar, 1. Here, our shift and add multiplier would have done 2 additions. This guy will do 2 additions and 2 subtractions. So in this case, it became worse. But on an average, you can expect an average case, we can expect fewer addition or subtraction than the shift and add. There is no, I mean, sometimes it may actually do more than the shift and add. Is it clear? So let us multiply 5 and maybe 6. Okay, so we'll load accumulator with 0 and this guy is 0, 1, 1, 0 and 0, 1, 0, 1. So I've taken this as a multiplier and this as a multiplier. So we'll create one extra bit here which is initialized to 0. We'll compare these two. If it is 0, 0, we simply shift. Okay, so we shift A and Q. If you see a 0, 1 like this, that means you have to subtract. So here I have 0 and I have to subtract 5 from it. So 0 minus 5 is minus 5. It's a signed multiplication. So minus 5, you may remember, is 1, 1, 0, 1. This is minus 5. And this remains 0, 0, 1. Then we shift. And when we shift a signed multiplier, we also have to add a 1. Now we are seeing a 1, 1. We simply shift. Last but not the least, we see a 1, 0. So we add. So this is 1, 1, 1, 0, which is minus 2. Right? Minus 2 plus 5 is 3. Then shift. At the end, we will have the answer in the. So this I believe is, so this is 2 to the power 16, 2 to the power 4 or 16, plus this is 8. The next one is 4, and the next one is 2. So this answer should be 30. So it requires an adder or a subtract. I mean something that can do both add and subtract. So if you are looking at the hardware, then you will have to use A and Q, and you will have an M, and you will have an adder or subtractor. Which will require a control signal, right? And and the result of the add subtract goes back to the accumulator. There is a 1-bit register that we keep here, which is initialized to 0, and we compare that with Q0. So these two can be either 00 or 01 or 11 or 10 or 1. So in this case we shift. In this case also we shift. In this case we add and shift. I'm sorry, subtract and shift. And in this case we add and shift. So the control signal, there is possibly a controller which will take these values and decide to control the add and shift. It will control this signal. It will control the shifting. It will control the loading. So the controller will produce all the signals. The signal for loading M, loading A, loading Q, loading that 1-bit. Let us say we call this F, right? So it should generate these signals for loading M, A, Q, F. Then maybe it needs a counter to keep track of how many times we have done on this. The counter load also we have to control. Then decrement counter we have to control. Then add, subtract. This will take the clock and the Q. I'm sorry, reset. It will also take Q0 and F and produce the signals. Okay. So a designer will try to possibly design something like this. Okay. If you give a model like we have been doing, that is not synthesizable. Okay, it may not be synthesizable. The class is definitely not synthesizable. The other one that we wrote in the morning, that may be okay. That I think it can synthesize. Okay. Any doubts? So since we are mainly interested in the verification of this algorithm, we can just develop a class for it, which is
Sir,
much easier than trying to get
sir,
into the details of the hardware, etc. So we could say class boot. So what will be a function? And what is the function view? What do you think it might do? It may initialize A to 0. A is an internal register, let us say bit. See, if you want to make it general purpose and make n large, see, unfortunately, we could try that. We could try define n and n to be, let us say, 8. Maybe we can say n minus 1. So the function u will initialize A to 0, then count. So count it may initialize to 0. What are the other things it has to do? And that f also we need, right? Bit f. Another way to do is, you don't do anything when it is done and then give a reset function. Because we may have to do this. And here you could say reset. So this has to be possibly defined before because it doesn't understand reset until you see this. So it may give a complaint if I use reset before defining. Then we can do, clock. So when the clock is issued, you will check case Q0 and F. If it is 00 or 11, then we simply shift. Okay. So we say, see, we need to take A here and Q3 n minus 1 to 1. And since it's a, arithmetic shift right, we'll have to copy whatever is in A n minus 1. Okay. So it's going to be a arithmetic shift right. So all bits of A will be copied. And if the most significant bit of A was 0, we'll copy 0, otherwise we'll copy 1. Then if it is 0, 1, that means we add. So we take A and Q and we load A and A equals A plus M. The carry will be ignored. We don't care about the carry. And 2B10, here we just, there's no need for begin. Oh, we have two positives. This has to be done anyway. See, this has to be done. The shift has to be done in any case. So unfortunately, we may have to do it like this. And if it is 1, 0, we have to, instead of doing addition, we subtract. And as a result, you will have to possibly keep A to be a signed register. Otherwise, the subtraction will not work correctly. So we know how to clock, we know how to reset, we know how to. So if we have to multiply, we can create one load values. And we can take the bit n minus 1 to 0 of multiplier and multiplier. And our Q will be loaded with multiplier. A will be loaded, I'm sorry, N will be loaded with M. Industry and information. So we have the clock and we have the load value. Okay.
Sir, do we need to shift the LSB of Q to F also?
Hmm?
No need.
So they should all look the same. Mm.
Sir, what is F actually?
F is that 0, no? That I was storing that extra bit, no? This bit.
Okay. Sir, we are in product will have a multiplier, multiplicand, and we are accumulating. And in that F is come from any of.
F also has to be shifted. Good point. We have to also shift F. So Q fully we have to.
So why it is name F? Anything is there?
Why it's called F?
Ah,
You can call it anything. There is no specific.
okay,
We want to recode the multiplier. The multiplier,
okay.
if you see a 0, 1, we see that 1 bar, right? That effect is being created. See, I told you about
Okay.
this recoding,
Yes,
right?
yes, sir.
If you see 0, 0, it's simply shift. 0,
Yeah,
1 means 1 bar or subtract. 1, 0 means add, and 1, 1 also means okay. So when you see a
yes,
sequence of
yes,
zeros or ones, you don't do anything. But if you see a 1 or a 1 bar, we have to either do the addition or multiplication.
yes.
So if this is n bits and make sure that this is correct. This is 2n bits and this is n.
Sir, the F should come on the left side, isn't it?
See, we are shifting A, all of it, then Q, all of it. So F should be on the left hand side. So it is 2n plus 1 bits on both sides.
Sir, the right side, it should be carry, I think.
So A is n bits, Q is n bits, 2n bits plus 1 bit. So here also we have 2n plus 1 bits. On both sides we have the same number of bits. So hopefully this is okay. Is that okay? See now. And okay, I think that should fix it. Everybody happy? This one. So now we write the test bench. So module test, boot test. So boot, let us say BM, boot multiplier. And maybe initial. So here BM is initially new, and then we have to reset BM. Then we have to apply so many forms. I think when we did new,
Sir, I have a query. Sir, can you hear me?
yes,
When we add these numbers, no, like a plus m, it may generate a carry. So we are ignoring that in this case.
yes, I told you, no, it is ignored.
Yeah. Okay.
So we have to do BM dot clock. Then maybe we have to have a display. There should be a task, I think. Even this is actually a task. This could also be a task. This can also be a task. So display will simply display everything. And, okay. So in error, we can check if employer multiplied by MCAT is not equal to product, then display. So after the clock, you can maybe display. And then at the end, we can say, and we have,
Sir, VM, not P.
huh?
Our object name is VM. No, sir. B dot.
BM. Reset. BM dot reset. We have to first load values. Oh, you know what? This is
Sir, reset function name RST. No? Sorry. Sir.
very load values. Load values. Mm, mistake. This non-blocking when you use it causes problems. So now it's okay because without completing the add it was shift. Can you see now? So we loaded A with 0, Q with 5, multiplicand was 6, F was initially 0, and then count is the count should not be 0. We are not doing anything with the counter. Okay, we should do that. But I am not loaded the count should be initialized to n, right? That is happening here. So we loaded 0, 5, F is 0, count is still. Why is the function, why is count not getting loaded? In load values, what am I doing? See, this reset is not working, guys. Yeah, this call to reset is not working. That is what it is saying. No? See, something it is saying. This dot reset. So this reset is never done. So it's like this is not there at all. It will just okay. Now let us look at it. So initially we saw 0 and 1 here. So we have to subtract, right? So we have subtracted 6 from 0, and that gives you a minus 6. Minus 6 and then followed by shift. So here, unfortunately, you are seeing both subtract and shift. So you will have to do it by paper. When you are seeing a 1 0, that means we have to add and shift. So this is the result of add and shift. When we are seeing a 0 1, so we have to subtract and shift. Then we are seeing a 1 0, so add and shift. Then we are seeing all 0 0, so just keep shifting. The last one, I think you have to subtract and shift. Okay. So we'll try another example. Let us say 25, or let us say 5 and minus 6. Let us say. That should give you minus 30. So this is minus 30. Okay. There is an error also is coming. That sign we have to do. We have to say multiplier has been declared as sign. So sign. See, if you write, this is a negative number because there is a 1 here. So if you do the 2's complement, you will get 0, 1, then all ones, then 0, 0, 0. So we'll have 3 ones followed by 1, 0. That I believe is minus 3. But why is this giving this not? Sorry, I think sign should be here. Which is weird because I have declared everything as sign. Now there is one. Okay. So try a few more test cases. 255 minus 1. The 255 is the largest negative number that we can represent. Mm. Let us try 128 or 127 and minus 1. So 127 is the largest positive number you can represent. And minus 127 will get. Okay. So this is minus 127. If you take 1 here, all of these will become ones when you do the two step.
Sir, take both negative.
Both?
Negative.
Both negative 1. Minus 5 and minus 6. Even this one. Okay. So you can do a little bit more testing. Okay. I think we have to try multiply by 0, etc., etc. So try. Okay, I'll give this code to you, and I want you to test it. You can try random testing. You can try, creating your own test cases. Any doubts in this? I have not been looking at the chat, so
Sir, lunch break is there.
chat on right side should there be carry? No. Oh, you want a break now? Okay. Sorry. Let's give a break, and when we come back, we'll continue. So, how long should the break be, Vineet? Vineet? How long should the break be? I didn't realize it's already 2:30. Okay, 30 minutes. Fine. We'll give 30-minute break. We'll meet at 3 o'clock.
The code is